Today is maximum and minimum problems using multivariable functions. So, back from Calculus 1, we used the first derivative test by testing the critical values for increasing and decreasing or decreasing and increasing to get either a max or a minimum respectively. Well, in Calc 3 we're not going to use such a thing, that first derivative test. In fact, we're going to use the second derivative test, which relies on concavity. You know, when we have some function that is concave down, really has a minimum. And when we have a function concave up, it has a maximum. And well, amongst other things, so first of all, let's define what a relative extrema is in 3 dimensions. So let's look let's do like the algebraic or formal definition of what a relative minimum is. So a function f of x, y has a relative local maximum at a given point x naught, y naught, if there is some circular region centered at that point such that f of x, y is less than or equal to f of x naught, y naught. Well, that looks like a lot of symbols. How about we do a picture? Well, so this is the picture, the point that we claim it's, in this case, the maximum. And well, we consider a circular region, all right? And this f of x, y, it's every single point, any point on that circle. However, you can think of this circle as pretty much like a hill. Let me see if I can draw a hill. And well, this is a maximum point, and this is the circle that's going to go backwards. Well, so every single point f of x, y, it's actually less than that point that we claim it's the maximum, right? So in other words, we're at the top of the hill, we are at the maximum, and the minimum follows a very similar definition, but in this case we have that point, well, that minimum point, and f of x, y would correspond to every other point that it's actually above that point that we claim is the minimum. So just like functions, one variable in Calc 1, and well, I don't think we did anything in Calc 2 with max and mins. No, we didn't. So maximums and minimums occur at critical points, and those critical points are obtained by finding the derivative, the first derivative, setting the derivative equal to 0, and then do the test, right? Do the first derivative test or second derivative test. Now, in some cases, not all those points represent maximums or minimums. In some cases, we got the test to be inconclusive, or in some cases those critical values turned out being some of the discontinuities of the original function, depending on the kind of function that we're working on. All right, so let's find the critical points for the function f of x, y equals 4 plus x minus 1 squared and plus y minus 3 squared. So we're going to take the partial derivatives. In this case, so back in Calc 1 we took the first derivative. Over here we're going to take the second, the partial derivative of f with respect to x. Well, the derivative of 4 is 0. The derivative of, using this chain rule, that's going to be 2 times x minus 1, and the partial derivative with respect to y, that's going to be 2 times y minus 3. All right, well, so in this case, just the same way we did set the derivative equal to 0, we will set, in this case, the two partials equal to 0. So that means we will set this equation, this derivative equal to 0, 2 times x minus 1 equals to 0, and that's 2 times y minus 3. equals to 0. This means, well, divide both sides by 2. We're going to get x minus 1 equals to 0, which means x equals 1. And over here, divide both sides by 2. Y minus 3 equals to 0, and y equals to 3. So the critical point is going to be the point P 1, 3. However, well, we need to get an idea of whether this point that we obtain, it's a maximum or a minimum. So in this case, well, number one, we need to find the corresponding value of z in this case. So P of 1, 3. Well, what would be the value of z in this case? So 1 minus 1, that's going to get 0. 3 minus 3, it's also 0. So only the 4 survives over here. All right? Well, can we determine if this point represents, or what kind of extrema represents? What is this a minimum? Is this a maximum? Well, so far we don't have the tools to determine. Well, we will get those tools in a couple minutes. So by inspection, well, let's look at the function separately. For example, what if we had f of x equals 4 plus x minus 1 quantity squared? Isn't this a parabola shifted 1 unit to the right and 4 units up? And well, because the coefficient of the quadratic term is positive, well, it looks like a parabola opening up. What would that critical point represent? A maximum or a minimum? A minimum. All right.